I wish I had a better way to do that, but I don't. So in one of the first videos, I mentioned that I'd be doing one fairly brief one just on regulation alone. So this is that video. It's all about regulation of metabolism with extracellular versus intracellular regulators. I want to start with the extracellular regulators. Basically, all you need to think about with that is hormones. So this pulls in the endocrine system. Our two main hormones, and they're going to oppose each other with their functions, insulin and glucagon. Glucagon and epinephrine do the same thing. So associate epinephrine with glucagon, but the main two you need to know, insulin and glucagon. Insulin is going to drive your anabolic pathways, or it's going to be produced in your fed state. The other video talked about all your fed state pathways. And then glucagon is going to do the opposite. That's going to be your fasted or your hungry state hormone that's going to say, hey, the body needs more energy, so we need to start breaking down our storage forms, breaking down our proteins, fats, etc. So they have two completely opposite jobs. But here's the catch. They're hormones and they don't enter the cell. But where's metabolism occurring? Within the cell. So there's got to be some way for these hormones to communicate within the cell. So I think in another video I made the analogy of it's like you go to a house and you knock on the door and you have to relay your message, but you can't enter the house. So that's the same idea. Insulin, glucagon, epinephrine, they go to the cell membrane, they send a message through that needs to be done, and that's through the second messenger system. A little bit of that's covered in some other classes, so I'm not going to bother doing much of that with the whole PKA, adenylate cyclase, cyclic AMP, all that system. Just know that that's what I'm talking about with glucagon epinephrine to activate that PKA or protein kinase A system. Okay, so with insulin and glucagon, if they're both relaying a message into the cell, there has to be something that differentiates. The outcome has to be different because remember, they oppose each other. And they're not present at the same time. The body knows when to secrete one versus another. So they have to get two very different messages into the cell. And the way they do that is largely through something called phosphorylation. So that's just using a phosphate group. It's going to be one of your, if you remember back to Bio 1, those transfer enzymes. It's going to be one of the transfer enzymes that transfers a phosphate group to and from the substrates that we need to regulate, or the enzymes that we need to regulate. So insulin, get this in your head now, insulin dephosphorylates. That's insulin's MOA, mechanism of action. It is a dephosphorylation. So when insulin goes to the cell door and says, hey, I have a message, this is what needs to go on, what happens is that there's just rapid dephosphorylation of these enzymes that it's regulating. And when those enzymes are dephosphorylated, if it's an anabolic pathway or if it's a pathway that's going to be stimulated by insulin, those enzymes are active when they're dephosphorylated. The opposite of that is true to avoid this whole futile cycle. If we're making something, we don't want to be breaking it down at the same time. So if insulin dephosphorylates all of these enzymes and it activates the ones that it needs to, the pathways that it needs to stimulate, it's going to do the opposite and inhibit the pathways that it doesn't need to stimulate via dephosphorylation. So glucagon is going to do the opposite. I'll try to say that in a few different ways. It's never simple. I don't know how best to say it simply. But glucagon is going to do the opposite. Basically, it goes to the cell and says, phosphorylate everything. So everything's getting phosphorylated, and those pathways that insulin or that glucagon is going to stimulate that break things down, those pathways are activated by phosphorylation. But the pathways that build things back up are now deactivated by phosphorylation. So they both of these hormones do one thing directly that then has a host of other indirect effects. So down here, I don't know if you can really see this color, but this is an example of, this is an enzyme and it's phosphorylated. So this would be driven by glucagon versus an enzyme that you cut that right there to make it dephosphorylated, and that will be the result of insulin. And we'll get more into that when I'll do specific pathway examples to kind of help hammer that idea home. But like I said, if anything else, get into your head now that insulin dephosphorylates, glucagon phosphorylates. And by doing those things, each of these can accomplish what they need to within the cell. That still avoids the futile cycle. So that pretty much does it for our extracellular regulators. Our intracellular ones are a bit more straightforward. Basically, you're thinking about within the cell, that's where the energy is, the ATP, the NADH, all those measurements of energy, the currency of energy within the cell. That's where those things are, and so we're already in the cell, and those things can communicate directly with the enzymes that they need to regulate. The second idea with intracellular is going to be your allosteric regulation. Again, pull back out your Bio 1 notes if you don't remember what allosteric is. I always made the analogy of, if your enzyme is a Pac-Man, that's Pac-Man here, and it's going to go through and it eats all the substrates that it needs to. So this is the active site, so that's active. But then Pac-Man on the backside has an allosteric site. So Pac-Man, its normal job is going to be to bind things at the active site, its mouth, right? But if something's going to bind allosterically, it's elsewhere. It's not the active site, it's elsewhere. So it's the back of Pac-Man. I don't know if I can call it Pac-Man's butt on camera or not, but it's what I normally would do. So with allosteric regulation, that says that, all right, remember back to this assembly line thing. We're making things, but product starts to accumulate because the body's not using it. Well, that product then can come back, and it's called a feedback loop. So it feeds back to the enzymes that are making all this stuff and says, hey, slow down. But they're busy. They're busy at the active site, so it has to bind allosterically. So these are our allosteric regulators, and those are going to be the things that are downstream or the products of your pathways. And that can result in something, another key phrase that you hear with this is a negative feedback loop. It's just saying it's negative because it's negating the action of these enzymes, and it's feeding back, and now you've got this loop going on. So just a way to control what's going on in the cell. So back up to the energy availability. When you're wondering, okay, if the question says, this anabolic pathway is stimulated by what? Well, if it's anabolic, it's making things. So it's going to be stimulated by high levels of energy that are already available, and that just tells the cell, hey, we've got all this energy, now we can go and make these other things with it. So that's kind of where the logic of these, especially these first two bullets, will come into play. So ATP and NADH, both of those are set. If you have a lot of those, that means that the cell has made a lot of energy. There's a lot of energy available to then go and do other things. So these two, if there's a lot of those, that's going to stimulate the body to say, hey, we can go do these anabolic pathways. So then, little question here, what hormone is going to be present with that situation? Insulin for the anabolic pathways. So then the opposite's going to be true of, let's say it's overnight, I wake up in the morning, I forget to eat breakfast, here I am, 1 o'clock because it was a busy day, and I'm super hungry, my body's blown through the glycogen, I'm in gluconeogenesis, starting to burn down my proteins. The body knew to do all of that because I had ADP and NAD plus more in surplus in the body because my body had already used my energy stores from any food. So these were what was present because these were low, and then my body knows, okay, we're in a state of we need to be breaking things down to try to get more of ATP and NADH. Calcium is just another common regulating theme. Just start associating that with glucagon and with catabolic processes. So if calcium's high, you're typically thinking that you have more ADP, NAD plus available, glucagon's high, the body needs to be finding other sources of fuel than what we've eaten for that day. So that'll about do it for the details on regulation, other than with specific pathways.